I'm appreciating your presence and try to talk a little bit about the necessary post-processing after inkjet printing for the industrial applications, and maybe talk about some misleading and misunderstandings which still are here, even the technology is started already several decades. After a short introduction, I've structured my paper according to what really is a required principal process after the inkjet drop has landed on the substrate. I talk about the major today's technologies and evaluate them in comparative way. And maybe there are some specialties we can find out of the adphosNIR technology. And after some applications, I conclude my presentation. I think the first thing is, and this is shocking to me all day, even today, in these times, that still people are not distinguishing that, or are realizing that inkjet is not a conventional, inkjet ink is not a conventional printing ink. And I think a lot of people are still not realizing that the water-based ink is not behaving like the offset lithography ink, which mainly consists of oil. The wetting, drying, and fixation process of a water-based ink, therefore, is totally different than a lithography printing process. And why is that? In fact, the lithographic process does not have a real drying. It is an oxidation process which is partially accelerated or enhanced by heating or by some evaporation in order to get a very little amount of solvents out. But the typical process is a heating process to get better oxidization, and due to the mostly present existing heating drying units for that, we have a temperature which is above the temperature that the moisture in the paper substrate is fully dried off, and therefore we have a fully dried off substrate. And due to the long time for this heating process, we have to have a post-processing to get the remoisturing or even a siliconization on this damaged substrate in order to handle the electrostatic changes as well as some tackiness for further processing of these materials. When we talk about inkjet, I think we have seen this already several times in the morning. I will do it again. I have now the perfect inkjet drop generator. That's assuming it's a perfect ink. And now my ink has been landed on the substrate. But what happens next? And that is, as we can see already, we have the splashing, which generates satellites. We have the shape is changing. We have, in a lot of cases, a bleed through. We have color bleeding. We have dot gain, and even the damage of the substrate. How do we handle that? And all that has to be handled with the post-process after the inkjet printing process. And that is simply called, we do drying. But the drying process, this so-called drying process, is much, much more than a physical removal of the liquid to get a solid ink pattern. No, we have to see, we start first. Somehow, the droplets has to be set to the surface. We have to stop the mobility of this droplet. And at the end of the day, we also want to, second, we have to evaporate the volatile liquids. And since all the water-based, solvent-based inks contain, beside the water, also high temperature boiling alcohol solvents. So we have to think about these. And it is not just the evaporation process. We also have to remove this vapor from the printed substrate. And therefore, the exhaust moisture, to remove that out of the drying area of the printed product, is a crucial point. And I can tell you, out of the experience of 20 years upgrading, enhancing, and making systems performing as they should, the simple thing is to think about the exhaust and the ventilation system in an existing line. This is the easiest way to improve performance, even in the given configuration. And if we have all that run through, in some cases, yes, we are ready for further post-finishing, but unfortunately, there are also additional post-drying requirements required due to the fixation to the substrate. And in a lot of applications, we heard this already in the morning, a preparation of the substrate is necessary so that we can apply the inkjet process, the so-called pre-printing or pre-priming process. Most of the cases, at least for plastics, glass, a lot of coated papers require that as well. So the principal drying process starts from landing, at least to after the removal of the liquid, partially even in this area. And now we have to think about how that's done. As soon as a droplet reaches this, the spreading takes place. Now, differentiating coated materials, we have a two-dimensional spreading, which we've seen earlier this morning. Achim showed that earlier on the UV. If that takes time, the spreading destroys already your printed pattern, even in UV-based systems. That is just due to the fact that the liquid, low viscosity ink pattern is not fixed in the drying, curing, whatever mechanism. So that's a dwell time before you start really the evaporation or the fixation process. Coated. In a lot of applications, we have a partial porous or fully porous substrate, and there we have a three-dimensional spreading. In graphical arts, in the older days, that was even the third dimension was the preferred way of drying. Take a porous substrate, let the water in, and we don't need dryer. Wait as long as possible. We don't get smearing on the support rolls. That's the best paper to run with. Maybe at low speed, at low ink coverage, and at low print quality. We were talking about applying a barcode, applying a small number on a recycling paper. Nobody cared about quality. Nobody was intending to use this as a high-quality application technology. It was just ready to read it with a barcode reader. But today, we are using these technologies as high competition for conventional printing. And here we have already the first misleading point, and that is the typical penetration behavior of papers is within a fraction of a second. When we talk about decoration paper, that is even 50 milliseconds, and all the water is penetrating into the substrate. In typical today's graphical systems, a second and a half is the maximum until the water is decelerated in order to go into the substrate. But with this reaction of water into the substrate, we have a fiber-water reaction which leads to debondings, interfiber debonding, which generates immediately a swelling of the fibers, which, by the way, is damaged forever. It is irreversible. And due to that, we result in a permanent substrate waviness, which we can see if you would wait to see already that where it's printed, we have waviness. And this, and here is another mislead. People are thinking this waviness will be taken away by remoisturing after the drying. How do you want to remove the waviness if the fiber is broken? This is damaged, and you cannot get it back by any other post-process to get it smooth or get it flat. The only thing what you can do with this remoisturing and siliconization process is to get the moisture back in an over-dried material, which, as we saw also for the conventional ink printing, that the moisture in the paper can be given back, but not the waviness coming from the destruction of the fibers. The next misleading point comes that we have the absorption of water and glycol. And if you think about that today, we are applying 15 up to 20 grams per meter square of full color ink content on a substrate, which is maybe 50, 60 micron thick only, you can already see how much the paper is expanded due to the water and glycol, due to the liquid absorption inside of the bulk of the material. So that is generating, already depending on what inkjet arrangement, inkjet configuration you are running, in register problems, specifically if you are running a process color from ABC color, and all the water has expanded, especially before the drying starts. And if you have a duplex printing, you come to the second point. The dryer now removes this, changes eventually by overheating the dimension in the other direction, and then again this process starts from the second side, and the register problem becomes even bigger. And on thin papers, because of this high amount of water, liquid, you get a high bleed through. So the misunderstanding is that these problems of misregister is not coming from any heat. It is just coming from the high amount of water. And that is also some of the misunderstandings why people are thinking intercolor drying should be avoided. The other thing is, stop the mobility is an important point, as we saw. So if we wait a long time, if we have a smooth, slow drying, we cannot stop the mobility. So therefore, again, mislead is, if we are waiting, that means we allow the penetration, we allow the damage of the fiber. With this penetration, we change the pore structure in the substrate. The more penetrated the structure, the pore structure, in order to remove the water out again, you have to find different exits in that pore structure because partially the pigmented are blocking this original path. So we need a higher dryer power. And at the end of the day, due to this longer time, due to the higher energy, we get a higher dry out. And now, that's also something which is high required. That is, as I said, the evaporation to get the vapor, is one thing, but second, to remove the moisture out of the drying chamber is important. So the combination of evaporation and extraction is a very crucial part. And if you are heating one thing and put later on a suction zone, that is already the first problem, because you might have in between already recondensation on the substrate, and at least it takes more energy to remove. In a lot of occasions, even the extraction system is not sufficiently designed, and therefore it's not operating properly. In addition to these principal processes, we have to take into account the dryer configuration things, depending on what technology we are using. So the avoidance of condensation is crucial, as we said, but not only because of the energy. We have also the problem that if that's not properly done, the high boiling and the water vapor might drop back on the substrate, which happens quite often when we look about in enhancing systems. The other thing is, people are thinking, oh, we have a high temperature, now the substrate is hot, so there is an afterwards fuming. Like you come out of the sauna, you are still fuming. That's good because it's an additional drying afterwards. Leaves the system at dwell time. The dwell time only gives sense if you have properly insulated that and have added there a ventilation zone to remove this moisture which is coming out. Otherwise, it sucks back to the printed product and condenses, and it's wet again. And therefore, that's also something which has nothing to do with the principle. It's a technology of the dryer. The change of the original substrate, I think that's the most simple thing, that you should avoid as much as possible the original property of the substrate due to moisture content, electrostatical behavior, as well as rheological behavior, especially for the post-finishing processes, cutting, slitting, binding processes. There, the only way to get this somehow adapted again is by adding additional post-finishing healers. But as we know, this also is not giving us always 100% solution for it. Energy efficiency, I think that's trivial. I don't talk about that here. Size, we heard this from Patty, that for the application, especially for high-speed applications, the dryer size is also crucial for that. And what I think what has not been addressed here yet is the dynamic capability of a drying system. I don't want to wait an hour in order to get the system ready. I don't want to wait another time after changing a print profile to get the system back to operate, or I change my paper or my substrate from 50 grams to 80 grams, and I have to wait until my dryer is capable to run this. Or even worse, start from 150 grams, go to 40 grams, and destroy the paper if you are not waiting long enough and get the dryer power back. So the resulting printing quality, performance, as well as costs are all depending on what I've described before. But now, I said we were evaluating different drying technologies. And in the past, I only talked about the principal processes. Now, I mean, everybody is, and this is, I think, something which is well known for 100 years, and every household is knowing this, is the hot air drying process, which is driven by the temperature of the air compared to the substrate, by a so-called efficiency to this heat transfer, the thermal heat transfer coefficient, and the area of that. I think the best example for that is this one. This is the simplest hot air dryer. Can be very effective, but if you are in a hotel, in a lot of hotels, you can see differences in efficiency because it's not running as a high efficient air convection system. It is more or less as a simple flowing system. And the other thing is, I think you can easily imagine if you have to go away from your substrate because you have a very long dryer and you have to a non-guided area, there's almost nothing coming on here anymore. And therefore, you need a very high drying area in order to get the heat going through. And at the end of the day, this is even more efficient because it took only 10 seconds to get to the operation temperature. I can tell you, if you do this in a typical air convection dryer, it takes you maybe 15 to 20 minutes to do it. Yes, the Japanese like this. The greatest heat transfer coming through a hot contact area, a hot plate, a hot drum. I call it the iron principle. And I think, yes, it is pretty simple to control. But on the other hand side, I avoid that. A liquid ink to dry like that, I think that would always come to a damage on the substrate and a damage on the printed code, on the printed pattern, and finally on my system. So therefore, I have to do this from the back side. And if I have to do this, I have to heat up the full substrate from all the mass I have to heat up to get the heat through to that. And at the end of the day, the temperatures which are required are even already destroying the paper or make the ink viscous plastic, or even both. It is hot, I have to remove, but it's still smearing and not fully dried. And again, based on that, we need a high surface heat transfer area due to the limited temperature. Now we come to the great radiation technology. Radiation technology allows us to have a higher temperature and is dependent on the spectral heat absorption. Yes, great. But all these today's typical conventional infrared systems we are using require the heat up of the substrate. So not the energy in order to remove the water. No, we have to apply all the heat into the substrate. We have to remove all that by the exhausting vapor. And now we look about typical today's materials like plastics or paper. We have absorption characteristics of that for radiation. In the UV area, there's a very high absorption. That's one of the questions you had when you said, what about my UV? It is destroying partially, or could be destroying partially already by the heat. Absorbed use UV radiation for temperature-sensitive materials. And if we look in the Midwave IR, which is so-called the very effective infrared technology for drying, we have a high absorption as well. And now we look in the near-infrared range. We have a very, very low absorption of plastic, of paper, of glass, of textile, of leather. So this behavior is, for a lot of materials, a very beneficial property because the energy of the heating source of a near-infrared system is not absorbed very high in the plastic. But now we see why the Midwave IR is not very efficient. Because we see here, this is a typical, let's say this is a printed pattern. Outside is non-printed. And when we characterize this, the differentiation of the color and the differentiation of the unprinted area, we see there's almost no difference in the absorption except black, which means a Midwave IR system is blind for the color absorbed on my substrate. And that puts you to the point that everything has to be heated. And there's another nice thing of a Midwave IR heater. You almost can smoke a cigarette until the system is in operation condition, and I could wait another 2 minutes before I really heat up my hand. And it takes time in order to get it back. If we now look about NIR, yes, we have a differentiation, as you see in the color. Yes, the color absorption is less than in the longer wave IR, but if we compare the absorption of the color compared to the absorption of the substrate, we are even at yellow a factor of 2 higher, and for the others even more, and therefore you have a proper distinguishment between the unprinted and the printed area, which means the energy is mostly absorbed where it's printed. And that gets you to the point that if you apply a high energy density, that you get a very strong evaporation rate for the solvent and the water, and a very little absorption at that time in the paper, which is in combination of that NIR is applicable, like switching on a light on off, shows you immediately the high dynamics of the system with the adaptation of the power and the energy. Okay, here we have the next mislead, which is the most important mislead, which still today even the manufacturers of radiation techniques have not understood. Unfortunately, you need sometimes a chemist who understands that. Maybe they should hire some more of them. Midwave IR is a good absorber for water vapor. But NIR, and when we talk about drying, we don't want to deal with vapor in order to get this. That is the result. We want to deal with the liquid. And fortunately, the absorption of liquid water and the near-infrared spectrum is great due to the polar molecules we have in the water. And by the way, we wouldn't sit here, at least that relaxed, if the near-infrared would be absorbed by water vapor because the sun would not give us the energy through at a cloudy day. So therefore, I think this is the best proof for everyone to understand where the mislead comes from. Dryness definition is also something which I don't make a comment on that. In some cases, people are claiming we need a lower moisture content in the coated material than in the original. I mean, at the end of the day, why should it be lower? The point is, if you are running with a infrared, with a hot air, with a conduction dryer, you have to have much higher energy so that the water is removed and therefore the ambient moisture is dried out, and that's why you need at the end of, or you lead at the end of the day on a lower content than in the original stage. With the NIR, typically, we only run maybe 0.5% lower, except if we need to apply the dryer a second or a second and a half behind the printhead, and therefore we have to take out some of the water already in the bulk. And the last point of durability problems is rub resistance. People are thinking with the drying of on hot air or hot plate, they can remove a 200 degrees C boiling material at a temperature of 100, 110 or 120 degrees C. I think we don't have to be too much in these details. Even a longer dwell time might lead in several weeks. You might come to find some atoms or some molecules of the glycol coming out by room temperature. Yes, but there is no remarkable reduction of glycol by even extending the dwell time. There's only one thing, and that is something we have proven in the running experience, is if you are applying a very high heat pulse in a very, very short time, what we do with this strong evaporation rate of the water, we disrupt partially glycol molecules during this evaporation process. And that helps us to reduce the glycol content and to enhance the durability. And that can be even taken place if you do this very, very short next to the print head. You can even achieve that at temperatures much below the boiling point. But that's not evaporation of the glycol. It is physical disruption because of the molecules coming out with the vapor. Look at your butter you are putting in your pan, heat it on strong, and how the grease is coming out. What is that? That's the water in combination, the water vapor in combination with your so-called glycol. So I have to come to the point of the end. Applications. We can talk about that several hundreds in the printing industry has been done in the graphical arts. We can talk about that later on the booth. What I would like to finalize is we are talking about industrial inkjet. 3D printing is something where the special near-infrared can give you significant improvement, specifically no speed limit anymore for the melting process of the materials. And everybody is talking about printing direct to shape. And everybody was thinking we have to use UV. I don't see a reason why we have to use UV. If I take NIR drying solutions, 5 millimeter with 8 megawatt per meter square power, or if we talk about 1 millimeter in diameter to be applied with 50 megawatt per meter square power. So if you apply this on a robot, I think it is pretty simple to understand that I can run every speed which you can run with an application system to apply the ink on a substrate. Thank you very much for your attention. Sorry for my overtime. And I look forward to, thank you.